on the problem of school violence, and there'll be presentations by Professor Furlong from UC Santa Barbara, Professor Amy Barnhorst from UC Davis, as well as a couple of policy people from state government who will be commenting on the whole spectrum of school violence, ranging all the way from bullying to individual one-on-one violence to mass shootings. So an important, timely, and topical area, and we'll be looking forward to hearing what the panelists have to say about solutions. Finally, on June 6th is our quarterly undergraduate student research project presentation, and that runs from 12 to 1:30. I forget what the food deal is there. Lunch will be served. Okay. So the important stuff. Okay. All right. So now, it's a pleasure to introduce Professor Katrina Gesso from the Department of Agricultural and Resource Economics at UC Davis, where she's an associate professor. Professor Gesso did her undergraduate work at Princeton and her graduate studies at Yale, but in between she spent some time getting a master's degree at UC Santa Barbara, so she's fully UC credentialed. She's now obviously at UC Davis, and she investigates the intersection between human behavior and many issues in the economics of the environment and energy. So we look forward very much to hearing your talk. Thanks, Professor Gesso.
Thank you. Great. Okay. Thanks so much for having me. I'm really thrilled to be here. So what I want to do today is I want to give you kind of a quick 2-minute snapshot of who I am, what I work on, and why I think it's important. And then I'm going to kind of delve into kind of one of the projects that I'm working on right now. And so generally speaking, what I'm really interested in is how people and firms make decisions in the water space and the energy space. The way that I like to do this is I typically partner with utilities, so a water utility or an irrigation district or an electric utility, and then we kind of design an experiment to answer this question. So why do I think it's so important to think about consumer behavior and firm behavior in the water and energy space? Well, kind of broadly speaking, I think it's important along 2 dimensions. Dimension 1 is that one of the main pillars by which we're going to reduce greenhouse gas emissions is through energy efficiency and energy conservation. So I think it's really important to understand under what conditions and why people conserve energy or invest in energy efficiency. Second, with a changing climate, one thing that's going to happen is water supplies are going to become more variable, or I should say precipitation is going to become more variable. This includes an increased frequency and perhaps stringency of droughts. So one way that we can adapt to and mitigate against the costs of climate change is through the management of the management of water. And so in my research, I'm really interested in, again, in how users, this includes residential users, it also includes agricultural users, when and under what conditions they conserve water, and what's the role of water markets. So kind of within this broad architecture of my research now, what I want to jump into is my talk for today. So my talk for today is entitled Spillovers from Behavioral Interventions, Experimental Evidence from Water and Energy Use. And I should mention a unique feature of this work is that I'm an economist. Gabe Lade is an economist. He used to be in our department as a graduate student. Now he's a professor at Iowa State. And Frank Loge and Ned Spang, who are both engineers, right? So this is kind of interdisciplinary research in the sense that it's between economists, it's joint work between economists and engineers. Okay. So what's the motivation for this research? I'm going to argue that the motivation is twofold. First, water is a major consumer of energy in California. So roughly 19% of electricity use in California is from the water sector. Roughly 30% of natural gas use in California is from the water sector. Water uses a lot of diesel. Kind of why does water use so much electricity and natural gas? Well, this is in the movement of water. Think about kind of pumping it up those mountains. It's in the treatment of water, and it's in the heating of water. So end-use heating accounts for about 60 to 70% of water-related energy use. Given this potential linkages between water and electricity, there's a lot of chatter about what I refer to, or what people refer to, as the water energy nexus. Right? And the water energy nexus, there's a lot of talk about it, but it's not really well, at least in my mind, it's not really well understood. And so when I think about the water energy nexus, what I think about is what is the interaction between water and energy services. And if you go kind of and you Google this right now, what you see is there's a lot of ongoing pilot projects, including some that I'm working on, that are trying to think about or pin down exactly what this interaction looks like. One thing kind of we're asking in the water energy nexus is, can water and energy be effectively managed together? And under what conditions can water and energy be managed together? So are there instances where there's joint water and energy savings? Under discussion right now, whether water savings should be part of kind of the energy efficiency portfolio. And how do the cost effectiveness of conservation and efficiency programs differ when we start to kind of account for energy conservation in water conservation programs and water conservation in energy efficiency programs? Okay? So motivation 1 is this water energy nexus, the relationship between water and energy use, broadly. Motivation 2 is what I call spillovers from behavioral interventions. So I'm going to give you a running example of this. So behavioral interventions are an increasingly popular instrument to alter behavior. These include default settings, commitment devices, and social comparisons. And they've been deployed in settings ranging from healthcare, retirement savings, voting, charitable giving, or conservation. So an example of a default option could be, an example of a behavioral intervention could be default options for retirement savings programs. And so a default option for a retirement savings program, what would happen is, instead of opting in to a retirement savings program through your employer, you're automatically enrolled in that savings program and you're asked to opt out. Instead of opting into an organ donation program to be an organ donor, you're automatically deemed an organ donor and you're asked to opt out. So that's an example of a behavioral intervention. Typically, when we think or we study as an economist these behavioral interventions, what we think about is we think about the impact of the behavioral intervention. So stick with me for the running example of default options for retirement savings. So what we think about is we think about the impact of this this default option for retirement savings. We think about its impact on retirement savings. What we don't think about is its impact on other forms of savings. There is the possibility that what might happen is you're shocked or you're hit with a default option for retirement savings, and it may impact unexposed margins of behavior for what we call treated individuals or treated agents. So another example. If you're nudged into a healthy eating program, how does that impact kind of exercise behavior? What if you're nudged into a program whereby now you automatically or you enroll in automatic bill payment for your cable bill? Does that impact your decision to enroll in automatic bill payment for, say, your water bill or your electricity bill? So why does this matter so much? Well, it matters a lot because the welfare impacts and the cost effectiveness of a program may be affected by spillovers. And I'll be a bit more precise about what I mean by this in 2 slides. So the setting in which we're going to think about what we call cross-sectoral spillovers is going to be social norms for residential water and energy use. So social norms, and by that I mean social comparisons, are a frequently studied behavioral intervention. So the most popular of these that you may be familiar with is O-Power. And what happens in O-Power is you get a home energy report, and it compares your energy use to that of your neighbor. The intervention we're going to be studying here is what's called Water Smart. You get a home water report, and it's going to compare your water use to that of your neighbor. Okay? So social norms are frequently studied behavioral intervention. They've been studied in a number of different settings. Nowhere has a study of social norms been greater than in the context of water and energy use. So utilities, when the drought hit, were deploying them all over the place in California. O-Power is almost ubiquitous throughout California. And so this is oft deployed and popular conservation tool for utilities. So let's think about cross-sectoral spillovers here. We deploy WaterSmart, and we look at its impact on water use. Well, what's the impact that WaterSmart has on electricity use? Does it have an impact, right? This is kind of one example of where a water energy nexus may arise. Or kind of the opposite may happen. You can imagine WaterSmart getting hit or being introduced to people reducing their water use and actually increasing, perhaps, their electricity use. So, our paper, what we're going to look at is we're going to think about this cross-sectoral spillover in the energy and water setting. So we're going to ask, what is the effect of home water reports on electricity use? So we're going to look at home water reports that were targeted towards water conservation. And we're going to ask, what is the impact of this home water report targeted at water conservation? What's its impact on electricity use? We're going to look at overall usage, and we're going to look at patterns of usage. We're then going to think about cost effectiveness. How does the cost effectiveness of deploying these reports change once we also think about the energy implications of them? The second thing we're going to do is we're going to test, and this isn't a term economists love to use, the mechanisms behind the presence of spillovers. And I'll be more precise about that next slide. The approach we're going to use is we're going to use what we call a framed field experiment. So we're going to use, in other words, a randomized controlled trial. And to do this, we partnered actually with a water, electric, and natural gas utility. The data we're going to use for this project, just to give you kind of a quick landscape, is we're going to use hourly water and electricity use data. From the water utility and electric utility, we don't have kind of monthly billing data. We have hourly data for every single household in our sample on their water use and electricity use. We're also going to kind of complement this with a post-experiment household survey and assessor data. Okay, so let's jump in. So how and why might home water reports affect energy use? So water use and electricity use is really complicated. And when I say complicated, I'm thinking it's complicated for two reasons. Reason one, people have imperfect information about the price of water, about the price of electricity. They have imperfect information about how electricity kind of use, how appliance use maps to electricity use. That is, if you increase your thermostat, decrease your thermostat, that is, increase your air conditioning by 1 degree, what does that translate to in terms of electricity use? So people have imperfect information. Second, this experiment that we're going to talk about today was run during this historic drought. So people may be attaching to kind of some moral utility to water consumption. That is, not only do they pay an actual price for water, but maybe they feel bad if they use more water. So they attach some kind of moral price or moral tax to it. Okay? What these home water reports do is if kind of these biases are present and this kind of information asymmetry is present, what they might do is they might affect water use, right? So you get a home water report, and what it makes you do, first of all, is maybe it makes you look at your water bill. Now you have a better sense of how much water you're using, or you have a better sense of the price, so you're going to change your water use. The second thing it might do is maybe you get a water report, and it shows you that you use a whole lot more water than any of your neighbors. So you feel bad, right? And so now all of a sudden the moral tax you place on water is higher, and that causes you to reduce water use. But what we're interested in is why might home water reports impact energy use? So here are two reasons why we think it might impact energy use. One is what we call a mechanical relationship. That is, you receive your home water report, you reduce your water use. And when you reduce your water use, what you do now is you wash 1 fewer load of laundry a week. This also causes a reduction in electricity use because you're not running your dryer and you're not using your washing machine as much. This is what we call a mechanical relationship. Channel 1, mechanical relationship. Channel 2 is what we call a behavioral effect. So now you get your home water report, you reduce your water use, and you're feeling really good about yourself. So maybe you crank up the AC a little bit, right? That's what we call in economics moral license here in psychology. Under that channel, we'd increase our electricity use. The opposite is now you get your home water report, you look at your water bill, but you also decide now to look at your electricity bill or look at electricity prices. And so maybe electricity use would go down. But there are two reasons why a home water report might lead to a reduction in electricity use. Because of this mechanical relationship, because of this behavioral relationship. So how are we going to look at this? Well, the setting in which we're going to study this question is with Burbank Water and Power. So we partner with Burbank Water and Power, a municipally owned utility down in Southern California that's comprised of 23,500 residential customers. And what we did is between May 2015 and May 2016, ran an experiment. And this experiment coincided with a historic drought. Our sample for the study is we have 7,341 single-family homes. We took these about 7,500 homes, and we randomly assigned, I'll explain what I mean by that, we randomly assigned 2,782 to control. These households got nothing. They just did what they were doing before. We randomly assigned about 4,500 to what we called water smart treatment. So in this water smart treatment, what we did is we sent every other month for a year these households' home water reports. And what these home water reports showed them is they showed them, that household, how their water use stacked up compared to their neighbors. It gave them individualized recommendations on how to conserve water. So you can't see this here, but I've seen so many of these reports. I know what they say. Give them, say, soft recommendations, which is fill up your washing machine, and hard recommendations. Change out your landscaping. And they also provide some information. So if there were watering restrictions going on during this time, they convey that information. So every other month, they're sent these home water reports. Again, control, nothing. Treatment, get these home water reports sent to them every other month. So now, I want to just take 2 minutes to talk about the research design here, which is something kind of I think a lot about in my office, but I just kind of want to give you guys kind of what was going on in my head when I was trying to design this study, or when we're trying to think about the impact of water and energy conservation programs on behavior more generally. Well, so what we're interested in is we want to measure the impact of a water conservation program on water and energy use. So one approach, I shouldn't call it the naive approach, but one approach would be offer up Water Smart to every customer and utility. So some people will select in or choose to participate in Water Smart or a conservation program, and others will choose not to participate in that conservation program. And then what you're going to do is you're going to compare water use or behavior across people that choose to participate and people that don't choose to participate. Okay? So I'm going to show you how this translates kind of in a picture. Okay? Let's call the blue line people that choose not to participate. And let's call the red line people that choose to participate. You can imagine if this water conservation program got rolled out, maybe people who are more interested in water conservation more generally would choose to participate. If you compare people that select into the program to those that select out, what you'll see is that they're different. They're different in their baseline water use. So all of a sudden, we're moving along in time, and then the Water Smart program starts. What we have now is we have a difference in water use between households assigned to treatment and households assigned to control. The problem is this difference in use is attributable to two things. One, that these households are different. Two is the impact of Water Smart. So how do we get around it? Well, we run what we call a randomized control trial. So what we do is we take all the households in Burbank and we randomly assign them to either the Water Smart treatment or the control group. The idea is that prior to the start of the Water Smart program, these households on average look the same in their baseline water use. Then, once the program starts, we can attribute these differences in water use to the Water Smart program. So what does our sample look like? Well, what we have here is we compare the baseline electricity use in every month across control and treatment households. And we see they're similar. So I want everyone to be right now, and don't worry about this. I will explain it in kind of one word. It's what economists like to do. It looks complicated, but it's really easy. So what I want you to kind of have at your head, how home water reports impact electricity use. They could impact electricity use for two reasons, this mechanical relationship or this behavioral channel. The way we're going to do it is we're going to use a randomized control trial where we randomly assign households to treatment or control. Okay. Now, how are we going to compare water use and electricity use across treatment and control households? Well, all we're going to do is we're going to look at electricity use for every household in our sample in every single hour of every single date. And we're just going to take a difference in electricity use across households assigned to Water Smart and households assigned to control. That's all we're doing. We're just going to compare water use across households assigned to treatment and households assigned to control. So what in the world do all these other things right here mean? Well, we're really interested in doing two things here. One is we want to estimate an effect, and two, we want to kind of speak to how confident are we that that estimate is different from zero. So how we kind of get at that, when we get at that, is we try to throw in a lot of things here. This is time, a bunch of time variables. We try to throw in or include a lot of things that are really important in explaining hourly electricity use. What that does for us is it's not going to change kind of the difference in water use. It's going to kind of change the confidence with which we're able to say that this difference is meaningfully different from zero. Okay. So what do we find in our study? So again, all we're doing is we're comparing electricity use across households assigned to Water Smart and not. So in column 2, what we do is we're looking at the change in electricity use for households assigned to Water Smart versus control in the summer months. In column 4, we're looking at that change in electricity use during the peak hours of the summer months. So what we find is that Water Smart leads to a 1.5 to 2.5% reduction in summertime electricity use during peak hours. Now, if you're not kind of an electricity, kind of nerd a bit like I am, you might just kind of say 1.5% to 2.5%, no big deal. Who really cares? Well, O-Power, that specializes exclusively in home energy reports, the reduction in electricity use that they get is about 1.5 to 2.5%, or 1 to 4%. So the magnitude of the effect from these home water reports, magnitude of the effect on electricity use, is approximately or falls within the range of the magnitude of the effect from home energy reports. Okay. So next up, I'm going to go skip that slide. One thing we're able to do in this study is we have hourly data. So we're not only able to look at what happens to electricity use, but how customers' electricity use changes throughout the day in response to Water Smart. So what we find is that during the summer, customers are reducing electricity use between the hours of around 3 p.m. to 11 p.m. So the timing of when these reductions occur is really interesting for two reasons. Reason 1, if you're interested in electricity, another thing you know is that the wholesale cost to supply electricity varies widely, kind of within a day and across days. And what we're finding is that these reductions in electricity use are occurring during the times when it's most expensive to provide electricity in this system. So these reductions are occurring when it's most expensive to provide. These reductions are also occurring when electricity is relatively dirty to produce. So kind of the timing matters both from a cost perspective, but also kind of a dirtiness perspective. How dirty are the emissions associated with that unit of electricity production? So the timing impacts the costs and the emissions. Okay. Just want to keep track of time. Okay. So next up, what we want to do is I hopefully have convinced you that this Water Smart report led to a reduction in electricity use during those peak hours of the summer. Now what I want to try to kind of get at, not as cleanly, is why in the world these reductions are occurring. So we have this mechanical relationship, that is treated households run fewer dishwasher loads, and we have this behavioral spillover. That is treated households turn up their thermostat. They get their home water report, they think a lot more about electricity use, and so they turn up their thermostat. We're going to try and tease out what in the world's going on here. So test 1, we're going to look at the timing of the treatment effects. So our operating hypothesis here is that if there's no behavioral spillover, if it's purely mechanical, then every time we observe electricity conservation, we should also observe water conservation. Okay? How are we going to implement this? Well, we have hourly water data as well. So what I plotted out here are just kind of the average treatment effects for water. Just so you know, we're estimating about a 3 to 4.4% reduction in water use from the deployment of Water Smart in Burbank. So let's look at the timing of the day of these reductions. So this is the plot from earlier. On the right-hand side, I think this is your right-hand side as well, right? What we have is water use. So what do we find? Well, we find that during certain hours there's significant reductions in water use, and this these line up with my priors. That is, we're seeing big reductions when you would expect people to be irrigating. But interestingly, what you find is that the timing of the reductions in electricity use don't coincide with the timing of the reductions in water use. So we see reductions in electricity use when we do not observe any reductions in water use. So this is kind of feather in the hat one, that a purely mechanical relationship is not explaining the spillover. Okay. Test two. I'm just going to talk about it briefly because it's a bit of a mouthful and it's pretty imperfect. So in my ideal world, what I would have been able to do is I would be able to compare electricity use, we compare electricity choices that do not require water as an input across control and treatment. So how I would really like to nail this behavioral hypothesis is that I would look at AC use across treatment and control households. And if I saw that there was a meaningful change in AC use, that would tell me that there's behavioral channels at play. Unfortunately, I don't observe AC use. So what we're going to do is we're going to look at how the response to Water Smart changes with an increase in temperature. We're going to do this imperfectly. Why? Because we know that cooling comprises a large share of electricity use in our sample, and demand for cooling increases in temperature. That's what we're going to do. Kind of the thorn in the implementation of this strategy or this test is that water use may also be responsive to temperature increases. So what we're going to do is we're lucky enough that in our setting, Burbank, we're not lucky enough. One feature of our setting in Burbank is that there were predetermined outdoor watering restrictions. That is, households were only permitted to water on 2 days of the week. So what we're going to do is we're going to divide our sample into watering days and to non-watering days. And we hope on the days that outdoor watering is prohibited that this link between temperature and water use is broken. Okay. So what do we find? Well, I'm just going to race through this, but what we find is that the electricity response to treatment is increasing in temperature, but the water response exhibits no temperature gradient. So there's this kind of this systematic relationship between electricity use and temperature in response to treatment, but it doesn't exist for water. So this is kind of line of evidence 2 in support of a hypothesis that is not a purely mechanical relationship. Line of evidence 3. We were fortunate enough to get funding from the Sloan Foundation to design and conduct a post-treatment survey for the households in our samples. So what we did is after the study ended, we sent a survey out to households in the control group and the treatment group. And we asked them questions about electricity choices and conservation. Okay. And so what did we find? Well, what we find is that households assigned to the Water Smart treatment are significantly more likely to report that they turned off their light bulbs, they turned off TVs, that they participated in these electricity-consuming actions that require electricity but not water as an input. Now, economists kind of bristle at the use of these kind of these surveys, kind of these ex post surveys, for a number of reasons. And so what we view this as is just another piece of evidence to support our story. Purely mechanical relationship is not explaining the reduction in electricity use. Okay. Test 4. This is our engineering model. Okay. So what we did here is we developed, and this by we, I mean the engineers primarily, developed a simple engineering model. So you take a representative household in Southern California, and we built a simple model of their water and energy use. And what we do is we shut off the behavioral channel. Okay? And we say, let's take the estimated reduction in water use that we estimated, and let's simulate what the electricity reduction would be because of a mechanical relationship between appliances that use both water and electricity. Okay? So, again, what we're going to do is we have a model of a representative household. Let's imagine that there was a 3.5% reduction in water use. What would be the accompanied reduction in electricity use that would simply occur from that reduction in water use? Because you're using your dishwasher less or your washing machine less. Okay. So what do we find? Well, what we find is that only 26% of the estimated reduction in electricity use can be explained by mechanical spillovers. Then what we do is we start to throw the kitchen sink at the simulation. We make a bunch of kind of implausible but still useful assumptions. So in assumption 2, what we assume is we assume that the 3.4% reduction in water use that we estimated, we assume that that whole reduction can be explained by a reduction in clothes washers, dishwashers, and the accompanying use of dryers, because that also uses electricity. So what we find is that if the 3.5% reduction in water use that we estimate for each household comes exclusively from these two uses, then that could explain about 24% of the electricity reduction we estimate. Why do we think that this is implausible? Ooh, I wrote it down right here. Now I'm looking for it. Because for these households, they would have to reduce their use of dishwashers and clothes washers. If they reduce their use of dishwashers and clothes washers in response to WaterSmart by 25%, that would only explain 40% of our estimated treatment effect. The third thing we do is we say, what if everyone in our sample, great, had an electric hot water heater? In fact, in our sample, only about 10% of households have electric hot water heaters. But if everyone in our sample had electric hot water heaters, then only 81% of our estimated treatment effect could be explained by mechanical spillovers. Framed differently, if we assume that 10% of our sample had electric hot water heaters, they would have to reduce their water use by 45% in order for mechanical complementarities to explain the estimated treatment effect. The last candidate explanation was we were wondering if pool and spa users were explaining our result. That is, you get WaterSmart, what you do is you just kind of stop using your pool pump, right? And that seems plausible. If that happened, about 515% kind of the treatment effect could be explained by mechanical spillovers. So what we do is we run our exact same model as before, and we take, and this is comprised only of people without pools. And what we find is that these spillovers remain once we exclude people that own pools. So pool users are not explaining our reduction in electricity use. So hopefully what I've convinced you of now is that a mechanical spillover is not exclusively at play. So the last thing we're going to do is we're going to think about cost effectiveness. What do these spillovers mean for the cost effectiveness of this behavioral intervention? So what we do is we look at the savings compared to the cost of WaterSmart exclusively along the lines of water savings. And so here, it's $2.91 per person per year. So they pay off kind of even on a water perspective, simply from a water perspective. But then if we factor in or monetize the electricity savings, what those amount to is $1.13 per person per year. So the incorporation of these electricity spillovers increases the cost effectiveness of this policy by about 40%. If we then go on to kind of factor in or account for the temporal heterogeneity, that means differences in the timing of when these electricity reductions occur, that's what we're going to do in panel B. What we see is that the electricity benefits further increase. Why is this? Because now we're starting to account for the fact that these reductions in electricity occur, when these reductions in electricity occur, it is also most expensive to provide electricity, and electricity is relatively dirtier. So the implication of that is that there's larger local externality benefits, and there's larger wholesale expenditure savings to the utility. So now, what we find is that the incorporation or inclusion of spillovers in our cost effectiveness analysis increases the benefits of this policy by about 62%. I also just want to state that this is not a welfare analysis. It is a cost-effectiveness analysis. So incorporation of spillovers increases the cost-effectiveness of this policy by 62%. Okay. So what have we learned, hopefully? Well, behavioral interventions spill over into unintended sectors. So in our setting, home water reports induced a 2.3% reduction in peak summertime end-use electricity. So we get a reduction in electricity use on the order of magnitude found from the deployment of home energy reports, and they're occurring when electricity is dirtiest and most expensive to provide. 2, what we think is happening is they appear to alter choices alter consumer choices about electricity use. It's not this purely mechanical relationship. Something else is going on. I kind of think about it, I have one on me, is kind of the home water report is working as a rubber band on your wrist, kind of hitting you, causing you to think about electricity use, perhaps. This work also points to what I think about as the limitations of a partial equilibrium framework. Right? If we just think about the impact of home water reports on water use, or the impacts of a healthy eating program on eating patterns, right? We're kind of looking at the impacts of these programs a bit in a silo. So incorporating in our setting energy reductions augments the cost effectiveness by 60%. And I think importantly in the water and energy space is it really kind of provides a grounded empirical data point to the collaboration, in support of collaboration and coordination in the deployment of behavioral interventions for water and energy. Right? These kind of utilities should be partnering up in the deployment of some of these programs. And the last thing I want to mention, kind of circling back to the water energy nexus. So typically when we hear about the water energy nexus, what we think about, we hear about is in terms of embedded energy. So we make all these assumptions and we say, great, that this is the energy required to kind of move this water and treat this water. What we don't know quite as much about is what's the impact of a water conservation program on end-use energy. And so what we're able to do in this study is something very different. We're able to kind of skin this question in a fundamentally different way. We're able to evaluate the effect of this water conservation program on end-use energy, right? And we find statistically significant and economically meaningful evidence that these home water reports led to a real reduction in electricity use. And I think kind of this really points to kind of, again, a feather in the hat kind of in this instance for the water energy nexus, or for kind of collaboration between water and energy utilities. But I also think it points to the importance of thinking about these programs in a more general equilibrium framework. Because in our context, they worked in the same direction. But you can imagine in other contexts, perhaps, things working in opposite directions. So thanks a lot. I really appreciate your attention.